Welcome at Technische Universiteit Eindhoven. My name is Professor Lou Vijs, and today we have another lecture in our series Golden Ratio. Today we have a kind of grand finale in the sense that we're going to use mathematics to do some serious innovation in fashion, revitalize the Pied-de-Poule pattern. By way of getting started, we have a look at this short video clip which has been recorded at the Wearable Sensors Lab at our university. These are the resources for today's lecture. There is this PowerPoint, there is a processing program, and there are external links to publications about this topic. This is the inspirational video clip which we shot today in our Wearable Sensors Lab at TUE. Wiskunde is mode. Today's lecture is about why innovation in fashion by math towards new pied-de-poules, then some mathematics of these new pied-de-poules, how to add symmetries, and a connection to topology by a notion called orbifolds. As usual, I will show you a small example in processing, how to generate tiles, and we will also show you one of the fashion results. Why innovation in fashion math? Well, if you have a look at this Pied-de-Poule pattern, and it's the same for other patterns, the fashion industry actually is not innovating as it should. Here you see an arbitrary search on what you can buy, and you see the Pied-de-Poules, they're all the same. They are black and white, they're meant for kind of formal contexts, and it's like this for decades. So what are the opportunities? Well, working with color, bringing in more fun and cultural elements, but also from the mathematics side. You've seen the fractal innovation in the first movie clip, but it's also an opportunity to look into symmetries and bring in more symmetries. There is also innovation at the technology side, like laser engraving, or a new type of printing which is called sublimation printing. Let's take as a starting point the basic Pied-de-Poule tile. Here you see it in black. It also appears in white, of course. As you know, these tiles interlock. So what can you do? Well, first of all, you can construct these strips, and then you can add more of these strips. And if you do it, you get this pattern, which is the classic Pied-de-Poule. If you look how it's constructed, you see that there are translations in this direction, there are translations in that direction, and there is the translation in that direction. So the tile has actually a contour which consists of 6 pieces, and pairwise these are translated versions of each other. That's kind of symmetry. Translation is one of the symmetry actions. What else can we do? Of course, here you can't do anything else than interlocking the tiles, but then you can put the next tile in a slightly different position. Here you see it's sloping, and that's because there are different translations. This is still the same translation, but this one is slightly different, and here you see the tiny edge is translated in a completely different form, which makes this Pied-de-Poule-like, yet it's different. What else can you do? Rotation. So if you add the second strip upside down, the next one like this, upside down, like this, we get a completely different pattern with a different flavor, although it's Pied-de-Poule-like. And looking at the symmetry actions, we see here a translation, but there is also a rotation around 180 degrees, and here you see yet another rotation point, another rotation of 180 degrees, and these rotations together with the translation, they define the actions of the symmetry. So this is another symmetry group. You can also work with glide reflections. So the next tile is not only rotated, but this is a mirror flipped version of the same tile. The original strip, the mirror flipped version. And you see here you get something which looks like the previous one, but actually is different because the symmetry actions are different. Here you see the translation, that's still the same. There is a glide mirroring, so this zigzag staircase is flipped and shifted at the same time, which is the glide reflection. And there is another tiny glide reflection where the short edge is glide reflected to different positions. It's interesting to ask how many of these tessellations are possible. Well, there are infinitely many, so that's perhaps too much for working with. So I formulated a few conditions. So the first condition is that it should be isohedral. Like this one is not isohedral. If you look here, the short tail of the tile is touching the body of the next black one, but then that one has a short tail which is dangling in the air. So different tiles do not have the same position in the pattern. They should, that's the condition called isohedral. So this one is rejected, disapproved, this is not symmetric enough. There's something else which could go wrong. For example, if you would put them like this, you see there is a huge black to black area. That's ugly, it's not Pied de Poule like. Same here, there's a huge white to white area. So we say this one has not the minimal same color contact, and we also disapprove that. Now, how many of these are possible? Well, there are two versions with translations only. There are 4 possibilities if you include rotations, and there are again 2 possibilities with combining translations and glide reflections. So here you see the 2 translation based, here you see the 4 possibilities with rotations, and you see the 2 possibilities with glide reflections in it. Towards fashion, that's what I promised you. So here you see what we did in the lab. All these 8 have been embroidered through digital embroidery. Here you see them draped in a muslin version on a mannequin. Still, it's too classic in the sense that it's still black and white, kind of formal. The idea though is good. Let me give you 2 definitions. The first is a sampler. A sampler is a one-piece artwork in which all instances of a well-defined and finite class of patterns are represented. So this is a sampler, and it's an interesting idea to make one garment showing all 8 combinations which we found. Rather than going into the formal, I give you another definition. A Hawaiian shirt, also called an aloha shirt, is a short sleeve, loose fitting, open collar shirt originally worn in Hawaii, lightweight fabric, colorful, bold design, flowers, leaves, birds, beaches, etc. That's what we're aiming at. So here you see the 4 symmetries again. And here I make a connection to a not so old theory which is called orbifold theory. Let me show you this book and also recommend the book. It's written amongst other by John Conway, a very famous mathematician. I met him once, inspirational guy, and so rather than just showing symmetries, I also show orbifolds. The orbifolds will look like topological structures, but here we give them the form of fantasy creatures. Like in traditional aloha shirts, you have like sea animals, fish, things like that. Here we have these next nature sea animals. Now the orbifold theory itself I recommend the book, but I will show you a few initial elements of the theory on the light board. Now I would like to tell you about these orbifolds. They have been invented by Thurston, and it's John Conway who developed their applications into this type of theory. My favorite way of starting with them is build it up slowly. Start with a simple tessellation, say a tessellation with a single tile, a puzzle piece like this. And well, more of these puzzle pieces are connected together. You see they fit like this, so it's a tessellation which is based on translation only. Now imagine a little flatlander who lives on this space. He can travel around in his tile, but he can also cross the border of his tile, and then he arrives here in another tile, and actually his whole surrounding is the same. It's like traveling in big cities. So if you're in Eindhoven, you can go to the Armani shop, and in the next street there is the Boss shop of Hugo Boss, and in the street after that there is the Chanel. So actually you have the Armani, Boss, Chanel. But in this tessellation, the tiles are the same. So here you have the same ABC structure. So whenever he has traveled from here to there, he recognizes as if he is in the same city. So what you can do is say, essentially, you don't need all these tiles. You need not travel to London. You can stay in Eindhoven. There is this one tile, and whenever our little creature, our flatlander, leaves it here, there's a kind of wormhole, and he enters back here. And if you do that, actually you wouldn't notice the difference. So this is what the orbifold theory says. Of this symmetric pattern, you just keep one tile and you identify corresponding edges. If you do this in topology, you have to stretch a little bit, but then you get a topological figure, which you know, of course. It's a cylinder, and then this edge has been glued. It's a kind of transition on the cylinder. So here, if we start with a single translation, this tile has only one symmetry action, which is translation, we end up with this cylinder. Now this was a very simple case just to get started. Let's take something more interesting, two translations. So I call them TT in the tradition of the Hayes tessellation types. So now we have the tile, copy of the tile, but we also have copies of the tile here, copies of the tile in two directions. And now our little creature can travel in this direction and get here, but he can also travel downwards, and then he gets here. If we reduce this to a single tile, identifying the edges, then we identify the lower edge with the upper edge and the leftmost edge with the rightmost edge. And now you may recognize the nature of this little flatlander. It's a Pac-Man. Whenever the Pac-Man leaves the screen at the right-hand side, he enters back here. And whenever he leaves the screen here, there is another magic wormhole, and he comes back here. What does that mean topologically? Well, programmers know that. They say if you glue the edges of a square, you get a torus. A torus is what looks like a donut, something like this. And then the edge, it has been stretched a little bit, but then the edge is here. And now you see the Pac-Man lives on this torus surface, and whenever he crosses the boundary, he's still on the same space. And then he travels back and he arrives here. But he can also make the other movement, like leaving here and then entering here. So there is no jump. Everything has been glued together. It's a smooth surface, which in topology they call a torus, a donut. And what the orbifold theory says is that actually for all of these tessellation types, wallpapers, if you have symmetry actions, you get another typical characteristic 3D object. Now we are going to test the same theory with another symmetry action, namely a glide reflection. Consider a tile like this, where you can see that one edge is a glide reflected version of the other edge, and it tessellates like this. So this is a nice tessellation based on glide reflection, the glide reflection going from left to right, and of course it flips. Now consider the Pac-Man living here. Pac-Man crossing this boundary. Okay, now he's here. You're living in the tessellation. Many copies of the same tiles, the same cities. Now let's try and reduce again the world to a single tile, which looks like this. And now I have to identify corresponding edges. So this edge, starting from the top, short piece, long piece, should be identified with this short edge, puzzle, bulb, long piece. So they are matched, but in an upside down manner. Now consider the Pac-Man. Pac-Man is here. He leaves the tile through a kind of magic wormhole. He appears here. But he appears like this. He's actually now at the back side of the same puzzle piece. He's walking at the other side. This is typical for the tile if it's connected because of its glide reflection. And what is the topological figure which belongs to this? Well, try a second for yourself to guess. If we stretch it and we connect this to that, giving it a twist, we get this Möbius strip. It kind of looks like this. And if you walk on the surface, after a while you're walking on the back side, and then if you go around again, you're walking on the front side again. So this is where the edge would be, and the Pac-Man, if he begins walking here, after a while walking here, he'll be on the back side of it. Perhaps you can see a little bit shine through. This is the eye. Here it is. And then if it goes around again, it's flipped. So here we get the Möbius strip. Yet another topological figure. I'm not going to do all of them in so much detail, but let me give you the main flavor of it. If we have glide reflections and also translations, we get a 3D figure which is known as a Klein bottle. It's like the Möbius strip, almost an impossible figure. It kind of self-intersects itself because it doesn't have a proper notion of inside and outside. This gives a Klein bottle. And if we take a rotation combined with a translation, we get something which is known as a pillow. So it's somewhat like an envelope. You can blow it up if you want, but the typical thing which also normal envelope have is that here you have this cone point. So the torus is smooth, even the clay bottle is smooth, but the pillow has these cone points, and it's a pillow depending on the tessellation. Like in the case of the Pied de Poule, we have a twisted pillow. So this is the basis of the orbifold theory, namely identifying corresponding edges, you get these figures. Essentially, this is also what we need for the Pied de Poule, because we have 8 Pied de Poule types. So we have the one with tessellations, with translations only. We have 2 of them, and they give rise to the torus. We have the one which have glide reflections and translations. They give rise to a clay bottle. And we have the ones with rotations and translations. Actually, we have 4 of them. And they give rise to a twisted pillow. So in that sense, these fantasy creatures which I had, they have a very deep topological meaning. So I will give you a summary of this orbifold approach. It starts with symmetry actions. And you know, we have several types of symmetry actions, like translation, rotation, glide reflection, and of course also the ordinary reflection without glide. And if you take any combination of these, then you get either a wallpaper or if the tiles fit without space in between, you get a tessellation, also called a tiling. In fact, you cannot take any combination of these. Some combinations are compatible, others are not. There are 17 possible combinations, and these are the 17 crystallographic plane groups. That's where the group theory comes in. They should be compatible. The rotation of a rotation should still be a member of the, this group of actions. And these actions, they live in a 2D space. You can do all of this in the Euclidean plane. It's a two-dimensional thing. If you have these wallpapers and these tessellations, particularly with the tessellation, you can move on. You can turn the wallpaper into a tessellation if you want. And then what you can do is you can keep just one tile. And you identify corresponding edges. Identify. And you identify those edges which are transformed one to the other by the symmetry actions. If you do that, you will get this concept which is called an orbifold. For example, a torus or a clay bottle or something like that. And the funny thing is that this belongs to topology. And if you want to visualize them, you can work in 3 dimensions and, for example, make them by 3D printing. You have to consider how you will stretch them or not stretch them. And this is a very deep connection which Conway helped develop between the 2D space symmetry groups and topology. This is a notion which we translated in our fantasy creatures and which we will embed in the Hawaii shirt. Next, I will show you an example in processing. You know, processing, it's kind of Java, but it's embedded in such a way that it's optimal for creatives. In this example, I will show you how to generate the contour of a pied-de-poule tile using something which is called Compass Turtle graphics. It has been designed particularly for this purpose. Actually, there is not a single tile. The tile is parameterized by a number, capital N. If you choose capital N equals 1, then you get the smallest version, which we call puppy tooth. But then for 2, 3, 4, 5, etc., you get the entire family. Here you see the beginning of the program, and there is one special turtle T, which is a compass turtle, and the constant step being 10, that defines how large the tiles will be. In this case, capital N equals 3, and in the setup, the screen gets a certain size. It's a white background, and the compass turtle starts at a certain position, which is a bit tricky. It's arranged in such a way that it will always appear in the center. The action is in the draw routine, as usual. And here you see the draw routine. Mention the compass rows. So we have 4 directions: north, east, south, west. And sometimes we make zigzag trajectories, like going east and then south and then east and then south, and that a number of times. So here you see the turtle in action. It goes 2 steps to the north, it goes 2 steps of the east and south types, it goes 3 steps to the east again, it does 6 steps in the east-south direction, it does 3 steps back, etc. In this way, the program shown here, it's a Compass Turtle graphics program, will produce precisely this tile. Now, where do you get this Compass Turtle? Well, that's under the other tab. It's object-oriented programming, so it's a class called Compass. Each object has an X and a Y position, which are initialized by the constructor. And then by example, I show you the north method. So if you call capital N for north with lowercase n being the number of steps, then of course there is a for loop doing something lowercase n number of times. And what this does is just making a vertical step, so keeping the x the same, and from the previous y to the new y, and the y is updated by this number n. And you can do the same for south and east and west, and if you can do south and east, then you can also do southeast. So this is the essence of this compass logo. You know, classical turtle graphics invented in the logo programming language, there everything is relative. The turtle has no clue about absolute position. It always works relative to its position, and it also has no notion of orientation. It just turns how many degrees you tell it to do. This one is relative regarding position, but it's absolute regarding orientation. It knows where the north is, and you can tell it to go there. Now we're going to run the program. So this is the classic tile. We can shrink it. We can shrink it even one case further. So this is the smallest one, the puppy tooth. You can also, if you see a poppy tooth, you can also say these are little windmills. It's another gestalt, but this is what the Poule theory says. We can also make larger one, larger, even larger. But rather than staying in the black and white, the next step is to go towards the fashion results, bring in this tropical theme. One ingredient we have already, the fantasy animals based on orbifold theory. Here you see the sampler. You recognize the 8 Pied de Poule types, you recognize the sea animals, you recognize other tropical elements. We have to choose colors, so we could go for very saturated colors. Actually, we will choose to be slightly more subtle later. And then we have been exploring production techniques like 3D printing, laser engraving, and sublimation printing. Here you see the sublimation printing. That's something new. Printing happens on special paper, and then the ink is transferred by heat and pressure. It can give very stark, strong colors, but also very subtle colors. And it also enables upcycling using existing fabrics or existing garments, giving them new life. Here you see how many samples we made, and here one of the results. So the recap and reflection is the pattern allows for many variations. The orbifolds, which live in 3D, capture the essence of the symmetries. We translated them into these fantasy creatures. We took inspiration from a certain type of aloha shirts called tapas style. And when I say we is not just me, that's also the people like Marina Tuters of the company BuyWire.net and another company labeled Buy. We also took advantage of sublimation, printing, and laser technology. Now it's time to show the result. So now the Hawaii shirt itself. It's my pleasure to introduce you Jingjia Li. She's a PhD student at our university. Today she's our model. You see the colorful pattern. We have chosen rather subtle patterns. The pocket has another type of saturation, so it shows the variation which can be achieved by sublimation printing.